All right, we got a 3-layered cake for you in this video. Hope you like cake. So, the lowest layer of the cake, or maybe the highest, I don't know, one of the sides of the cake, not perfect, is that the idea of continuity says that if a function doesn't have any breaks or jumps in it, we say it's continuous. So this function is continuous over here. Doesn't have any breaks or jumps. But notice right here, it does have a break. So it's not continuous here. Oh, it breaks again, not continuous here. Breaks again, there's a hole, not continuous here. But in this whole stretch, it is continuous. Now, a slightly more formal definition, the middle layer of the cake, says that a function is continuous at some point if the limit exists, the function exists, and they're equal. Okay? So if the limit equals the function, then it's continuous. And you can see that over here. Everywhere in this region, the limit value will equal the function. But right here, the limit is up here, and the function's way down here. That's why it breaks the definition of continuity. All right. And the top layer or the bottom layer of the cake for formality says like something's continue. Oh no, there's only 2 layers of this cake. It's the limit definition that has the higher layer. There's a really cool definition of the limit that says like for every natural number n, there exists like capital N such that, you know, if you have n bigger than capital N, then like the distance between, it's not important, guys. It's really not important. Let's talk about continuity and business calculus, okay? All right, let's do an example. Consider the function whose graph is shown below. Fill in the table. All right, this is pretty straightforward. What's the function value at different places? Let's start with this column. Fill in the function values. It'd be great if you wanted to pause the video and do it yourself. Highly recommended. But when our input is 1, our output is 2. When our input is 2, our output is 1. When our input is 3, our output is 2. And when our input is 4, oh, there is no output when our input's 4. There's a hole. The output does not exist. All right. So now we can do the same thing with the limits. As our input gets really close to 1, what's our output doing? Well, our output's getting close to 2. As our input gets really close to 2, what is the output doing? It's getting close to 2 again. As our input gets really close to 3, our output's doing 2 different things, right? From the left, it's approaching 2. From the right, the function's approaching 1. This limit, this 2-sided limit doesn't exist. The 1-sided limit existed, but not the 2-sided limit. And lastly, as our input gets close to 4, our output is getting close to 2. So, which of these points are continuous? For continuity to exist, the limit has to exist. The function has to exist. And they have to be equal. So right off the bat for continuity, that's not continuity. That's not continuous because the limit doesn't exist. That's not continuous. The function doesn't exist. This isn't continuous because they're not equal. This is the only place. Well, that's not true. This is the only part of the table that's continuous. This function is actually continuous in infinitely many spots. But which of these points are continuous? Only the point where x equals 1. And again, I know we have the letter a here, but a represents an x value. A represents an input because of this, as x approaches a. So we're going to say it's continuous when x equals 1. We could say it's continuous at the point. I'm writing behind my head, aren't I? At the point 1, 2. That's the y coordinate there. And that's how we could answer that. Whoa, lots of words coming up. But these words have good news. So, if the limit is a number, oh, this is where we talk about 3 kinds of discontinuities. All right. So, there's a hole. Before we even look at the words, we've talked about holes before, right? Holes, which of these do you think count as a hole? Well, if you guessed here and here, you'd be right. These are holes. And without even reading the words, which of these do you think is a jump discontinuity? Well, it jumps right here. This is a jump discontinuity. And there's a third type called an infinite discontinuity, which is just when the function goes off to infinity. We won't use those too much, but that's all this definition is saying. All right, how do you recognize a hole, also known as a removable discontinuity? How do you recognize a jump discontinuity? And how do you recognize an infinite one? We're not really going to talk about it, but you have it there if you need it, because I'll probably say these words. And then this is actually really, really helpful, okay? Most nice functions are continuous on their whole domain. So polynomial functions, rational functions, exponential functions, logarithmic functions, these are all continuous everywhere on their domain. And we can use this to evaluate some limits very easily. Why? Because if we know something's continuous, then the limit is just equal to the function value. All right. Very important, though, that we are still in the domain. Let's see this in action with example 5, and that'll be the end of this video. So, evaluate using the definition of continuity when possible. Otherwise, use an earlier method. So, let's look at this function. Is this function continuous everywhere? Yeah, right? This function is a polynomial. That means it's continuous on its domain, and its domain is all real numbers. So this limit is just the function value. 2 cubed minus 4 times 2, right? Because it's continuous, the limit is the function value, f of 2. Ta-da! This gets much easier very quickly. We get 8 minus 8. The limit's 0. As our input got close to 2, the output gets close to 0. The second one. Well, this is a rational function. So it's going to be continuous, right? Because we just said all of these functions are continuous on their domain. So it's a rational function, so it's continuous, so limit is the function value. It's continuous specifically on its domain, which is not all numbers. What's the domain? What are the possible inputs for this rational function? Well, we can't divide by 0. The domain is just everything except for -3. Because when our input's -3, it forces us to divide by 0. All right, well, 2 isn't -3, so we're good to go. This limit is just the function value. -2/5. Just like that. Now the last one's a little bit more complicated, because this is also a rational function. It's also continuous on its domain, but the domain here is all values except for 2. So this is not in our domain. Well, 2 isn't in our domain, but we can get really close to 2, no problem. So let's find this limit with Desmos. X minus 4 over x minus 2. What is happening to this function is our inputs are getting really close to 2. Well, hold on, let's zoom out a little bit. As our inputs are getting really close to 2 from the left, we're zooming off to positive infinity. As our inputs are getting really close to 2 from the right, we're zooming down to negative infinity. From the left is positive infinity, from the right is negative infinity. Oh no, this is an infinite discontinuity. Right? This function has a big jump. It doesn't get any bigger of a jump than this, right? From negative infinity down to positive infinity. And even if they were both positive infinities, that would still be an infinite discontinuity, right? If they were both positive infinities, we'd have something like this. Still not connected because the function value doesn't exist. All right, so this limit does not exist. It goes off to infinity. And that's how we can use continuity to make some of our limit lives a little easier. Got more example problems for you in the next video, stuff from the homework, so stay tuned if you want some practice with that or to see some more examples. Bye-bye.